Hello everyone, I am Golden Yashmi. I am here to present NAND and NOR implementation. So we found that we could implement general Boolean expression with these three primitives. What are that? And or not. In this section we will find that either of two gates, the NAND gate or NOR gate, can be used to implement arbitrary logic functions. Okay. Then the basic positive logic NAND gate is denoted by the following symbol. Okay, so input x, here we are noted it as x, y, z. Then the output x, y, z, the whole bar. Okay, this is the NAND gate output. The term NAND comes from not and, referring to the fact that the AND function is followed by an invert. So we will call this symbol for the NAND gate and invert. The small circle represent the invert function. If we apply De Morgan's law, we will get x, y, z the whole bar is equal to x bar plus y bar plus z bar. Then the application of De Morgan's law leads to the following symbol for NAND gate. Okay, so invert OR. Okay, we call this symbol the invert OR since all inputs are inverted. Okay, using that bubble. Okay, followed by the OR function. So note that both symbols are used to represent the NAND gate. It is sometimes more convenient to use one form over the other. So a single NAND gate with one input is degenerate and becomes an inverter. Then NAND gates can be used to implement a simplified sum of product form of a Boolean equation. So to say this, let us construct a two-level NAND to NAND gate function. Thus we will get this one. Okay, we are having A, B, C, D, 4 inputs. The outputs are A, B plus C, D. So the first level uses two NAND gate. Okay, two input NAND gates, so known as the AND invert symbol. The second level uses a two input NAND gate, so known as the inverter OR symbol. Okay, using the NAND relationship, we have G of A, B, C, D is equal to A, B, the whole bar, dot C dot D, the whole bar, then the whole bar. Okay, after this solution, we will get A, B plus C, D. In the previous implementation, note that the complement circles are on opposite ends of the same line. Okay, thus they can be combined and deducted. Okay, so here we are using the same level without the bubbles. This form of the implementation is the sum of product form. We may want to implement an equation like A plus B, C. The term A is degenerated and terms and must use an inverter to implement the function. Then the degenerate and term becomes an inverter. Okay, this actually we seen in the previous slide. It is easy to implement the complement of the function using NAND gates. Okay, so after the simplification we will get this. From the came up we can we see the F bar takes fewer littles to implement the F in S4P form. So F of W X Y Z is equal to Y dash Y bar Z bar plus W bar X bar plus X bar Y bar plus W bar is Z. F complement will be F bar equal to X Z plus W Y, and this leads to get this diagram. Then the basic positive level NOR gates, not OR, is denoted by the following symbol. Okay, OR invert X, Y, Z. Then using the bubble we will get X plus Y plus Z the whole bar. Okay, this is called the OR invert. So since it is logically an OR function followed by the invert. By De Morgan's law we have the following invert and symbol for the NOR gate. Okay, invert AND gate. Okay, so xy z using with the bubble, we will get the x bar dot y bar dot z bar. A single input NOR gate is an inverter too. Then NOR implementation. So NOR gates can be used to implement a simplified product of sums form of equation. To see this, let us construct a two-level NOR to NOR gate function. Okay, from the figure, using the NOR relationship, G equal to A plus B the whole bar, C plus D the whole bar, then the whole bar. Okay, A plus B bar the whole bar dot C plus D bar the whole bar. Okay, then after this we will get, using some Boolean simplification, we will get A plus B dot C plus D. So as with NAND to NAND implementation, you can also implement the complement of the function and use the another levels of inverter to complement it back to the desired function. Okay, for involution, okay, A bar the whole bar is equal to A. We already know that. And the De Morgan's law, we get the following useful equivalences. So A dot B, we can easily write it as A dot B the whole bar, and again one bar. We will get double bar. That means we will get again the A dot B. Okay, so in this we can again write it as A bar plus B bar the whole bar. Okay, for A plus B, we can write it as A bar dot B bar the whole bar. Okay, we already know that. Okay, so A plus B we can get using A plus B means A plus B the whole bar, the whole again bar. That means A plus B double bar, we will get the same answer as A plus B. Right, then A dot B the whole bar, we can write it as A bar plus B bar. Okay, so A plus B the whole bar, we can write it as A bar dot B bar. Okay, these simple transformation can be used to manipulate the two-level networks. The relations from the previous slide leads to the following transformation. Okay, so same as before, this is shown how the gates are transferred into the another gate. Okay, for the first AND gate, how it will transfer to the another gate using bubbles. That means bar noted it as bubble. Okay, so also to implement bubbles in series can be removed from the network. Then we need to consider whether the form of two-level implementation is to be sum of product or product of sum. Sum of product means AND OR function, product of sum means OR AND function. So complement output function, that is AND NOR or OR NAND, can be handled by complementing the function. So given a function f expressed as a Karnaugh map, we can use the same general procedure we have used before to minimize the function and express it in sum of product or product of sum form. Okay, given a two-level implementation, decides using the previous transformation to get into one of the below form. Then the following steps are very important to transform the function to the desired form. Okay. For AND to OR, sum of product form. Okay, we need to use circle once in the K-map and minimize. Okay, it's also used for NAND to NAND. Then the next one is AND to NOR. That means sum of product complemented. Complemented means we need to circle the zeros in the K-map and we have to minimize that term. We will get some answer. Right, for R to AND, that means product of some form, we need to circle. That means we need to group zeros in the K-map and minimize the SOP using the De Morgan's to transform to product of sum, also used for NOR to NOR. Then R to AND NAND, that means P was product of sum complemented. Okay, in this we need to circle once in the K map. Okay, that means we need to group once in the K map and minimize the sum of product using the De Morgans to transform the product of sum. Okay, for example, implement the function in R to R. This transform to R Nand product of some form with the output variable complementer. So we want to implement the complement of f in product of some form. That means we need to circle the ones and we need to minimize. Okay, for example, f equal to b bar plus a bar c bar. Using the De Morgan's law, we can construct the diagram, right? So f bar, the complementation, f bar equal to b dot a plus c. Okay, so in the left side we are noting that came up simplification. On the right side we are drawing the gate level diagram. Then and to NOR form is already in the consistency sum of product form with an output variable complement. So we implement the sum of product form of f bar. Okay, this form is equivalent to NAND to AND. That means we need to circle zeros in the K map and minimize the f dash. We will get f dash equal to b dot c plus a dot b. Okay, in the right side we are noting that zeros are grouped and we will get the answer as b dot c plus a dot b. Then the implement levels of gate is shown in the left side. Okay, thank you. Thanks for listening.